Hello everyone, this is Vashidhara. I'm studying fifth semester of Computer Science and Engineering. Today's subject is Theory of Computation, and the topic is about the research paper on conversion between six models of finite automata. So let's know about this research paper. The title is Conversion between six models of finite automata, and the authors are Michael Hospader and Galina Jirakskova. And the affiliations are called WAC Academy of Science. And the overview is about examining conversion complexities and the bounds between DFA, PDFA, NFA, MNFA, and AFA, and also BFA models. So the introduction to finite automata models are there are totally six finite automata, that is DFA, DFA, PDFA, NFA, MNFA, and AFA and BFA. DFA is nothing but deterministic finite automata, and PDFA is nothing but partial deterministic finite automata, and NFA is nothing but non-deterministic finite automata. MNFA is nothing but multiple initial state non-deterministic finite automata. And AFA is nothing but alternating finite automata. BFA is about Boolean finite automata. And the goal is to understand the conversion cost between these models. So let's know about the basic definition and preliminaries. These are recognized by DFAs but representable in various finite automata forms. The key symbols and notations are denoted by this sigma alphabet is denoted by this sigma symbol, and the state set is denoted with the capital letter Q. Fooling set of proving states are lower bounds. And the state complexity is minimum number of states required in the finite automata recognizing a language. So let's know about the Boolean and altering automata basics. Boolean finite automata is nothing but using a Boolean functions for the state of transition, and alternating finite automata allows the multiple transition functions per input. Coming to the conversion propositions, there are two propositions, that is proposition 5 and proposition 6 in this research paper, which talks about BFA to MNFA conversion with two n states, and proposition 6 talks about MNFA back to BFA with n states. Now let's know about the lower bound methods for multiple non-deterministic finite automata and non-deterministic finite automata. These non-deterministic finite automatas are recognized by Fooling set technique. Set technique defines the minimum states for recognizing the languages in MNFAs and NFAs. Lemma 18 says about any MNFA recognizing a language with a Fooling set of size n has at least n states. For example, we can take language L as a power n minus 1 requires n states in any multiple non-deterministic finite automata. Conversion challenges for unary automata. So let's know about the unary automata. What is unary automata? A unary automata is nothing but single symbol input languages. For example, a power n presents unique complexity. For this unary automata, we have key theorems like theorem 36, which describes about the conversion of unary DFAs to BFA, AFA, NFA, and also MNFA, which maintains the complexity within certain bounds. And Landau's function, which is nothing but Fn, helps to calculate upper bound Upper bounds in state complexity for unary automata. So let's know about the conversion in general case, which is nothing but multiple symbols, which is not a unary symbol. So in general case automata, we use arbitrary alphabet size, which is not unary. For example, a binary language recognized by an n state AFA requires at least 2n plus 1 states in an equivalent NFAs. The conversion complexity will be the tables provide a quick reference of for upper bound and lower bound based on the alphabet size. So let's know about the key lemmas and the proposition in this research paper. There are two important lemmas, that is lemma 7 and lemma 9. Lemma 7 explains about the conditions for BFA complexity based on DFA state and the requirements. And lemma 9 says about the relates which relates about a Boolean state complexity of unary language to its DFA state complexity. And the important proposition is proposition 16, which summarize the conversation between DFA, PDFA, NFA, and MNFA with the state constraints. So the summary of this conversion costs and bounds are, we can see that unary versus general case, which is nothing but the multiple symbol. Unary conversions are often simpler but can require more states. But in case of general case automata, it allows for the multiple symbols and also have the higher complexity. And the tables of the results says about the compact representation of state complexity for each conversion type and the optimal alphabet size, for example, binary or unary, noted where it impacts the bounds. So the conclusion and the future direction of this research paper are, the summary is about, we can know the conversion between finite automata models has well developed uppercase and lower bounds. And these techniques like fooling state sets and Boolean logic provides the insight into the minimal state requirements. And the future research for these topics will explore the additional complexity reduction method and also investigate new applications of automata conversion in the um, formal language theory. So that's about the future direction of this research paper. Thank you for watching this video.